The last point on this slide is that capillary pressure can be used to express the pressure of a phase in terms of a reference phase, and this is typically done in traditional finite difference solutions to the mass balance equation. So you will say, of course, PC, let's look at two-phase oil water is pressure in the non-wetting phase, which is oil, minus pressure in the wetting phase, which is water. So we can get an expression for the pressure in the wetting phase water by taking it to the left-hand side, and it's basically P pressure in the oil phase minus capillary pressure. And so you can write your equations in terms of this instead of PW, and that removes one potential primary variable, which could have been water pressure. And so we can continue to use oil pressure and water saturation as the primary variables for two-phase oil and water system. Here is your multi-phase flow mass balance equation. It's one equation for each phase when you're looking at black oil simulation. Why? Because we have assumed implicitly that each phase is made up of one component. And then for three-phase black oil simulation, it's oil, water, gas components and oil, water, gas phases. So those oil, water, and gas components are actually pseudo components because technically the oil component contains multiple hydrocarbon components, right? Same with the gas phase, it contains multiple hydrocarbon components. So we treat them as a pseudo component. And so we have three equations. When we look at actual compositional simulations, when you have multiple hydrocarbon components in just three phases, so in the oil phase, in the gas phase, and then you can have the hydrocarbons dissolved in the water phase. In those cases, you will see we will have NC number of equations for the number of components. So really, these number of equations here correspond to the number of the pseudo components, which are oil, water, and gas. And the equation looks like the equation you had before, except now you have saturation of phase alpha. In place of just density, you have density of phase alpha. Same here, velocity of phase alpha, and then flow rate of phase alpha. So it looks pretty much like the equations we had before, except that we use the subscript alpha for the phase in question, and then we bring in the saturation of that phase. This is the expression for multi-phase flow Darcy equation, basically. And then for the oil equation, alpha will be oil, and then you get one equation. For the water phase or the water pseudo component, you have the same equation but with subscripts W. For the gas pseudo component, you have the same equation with subscript G in place of alpha. So you have three equations. And you will see that pressure in the oil phase will show up in the first equation. Saturation of the oil phase will show up in the first equation. Pressure of water, saturation of water, pressure of gas, saturation of gas. So it looks like you have 6 primary variables. And then it's just 3 equations. So to make the system solvable, we need to add in constraints, and these constraints include the one we already looked at before, summation of all the phases. Summation of the saturation of all the phases should be 1, right? SO plus SW plus SG equals 1. And then the other is capillary pressure. So this is one equation. PCOW is PO minus PW, and then PCGO for oil and gas phases is going to be what? PG, the non-wetting, minus PO. So those are the three equations that make the equation closed. So you now have 6 equations. These constraints are 3 more equations, and then 3 equations here, making 6 equations. And then we simplify them by substituting these 3 equations in here, and then we eliminate some of these variables. So we will eliminate SO, we'll eliminate PW, and we'll eliminate PG. So in place of PW and PG, we use the expressions you will get for PW here, right, which I gave you before, and for PG as a function of PU and PCGU, right? That's how you eliminated these two. And for this, you eliminate it using the fact that saturation sum up to 1. So you already have SW and SG, and so SO is 1 minus the sum of those two. Basically. And so you end up with 3 equations and 3 unknowns. We already talked about these constraints. This is not important when you're using a simulator that is based on AD. But if you were going to program your derivatives yourself, then you will need to apply chain rule to differentiate the capillary pressure term, which I can post the video from 4056 if you're interested in this. But using MRS, we are not going to be using this approach. So for compositional simulation, we typically use those when you have volatile oils or condensate gas reservoirs, because the components are moving from one phase to another phase, and then you may want to account for injection of CO2, for instance, or injection of hydrogen. In those cases, you need compositional simulation. And then, like I mentioned before, you'll be writing the equation, one equation for each component. The components are referred to as the species. The fluxes of each of the species is summed up across all of the phases. So while you're writing the equation for each component, say component I, you will need to sum up that component across all of its phases, because that component can be present in the oil phase, it can be present in the gas phase, and sometimes dissolved in the water phase. So you need a summation over all phases. And so this is what the equation looks like. Remember previously we had phi rho for single phase, phi rho S alpha for multiple phases, and now for multiple components we will multiply this by xi. That's how it's written in the top family of simulators. But here it's written as CL alpha, which is the mass fraction. So this is mass fraction. Mass fraction of component I in phase alpha. Here is written as mass fraction of component L in phase alpha. So that's what these C's are. And what is it? It's basically mass of component L in phase alpha divided by density of component L in phase alpha divided by density of phase alpha. That is in comparison to mole fractions. So this is mass fraction. Mole fraction for component I in phase, let's write it in the same kind of way. Mole fraction for component I in phase alpha will be number of moles of component I in phase alpha, right, divided by number of moles in phase alpha. This guy is basically mass of component I in phase alpha divided by mass of phase alpha. We've just written it in terms of densities. And so that's the change in storage term with respect to time, or change in accumulation term. And then we have the Darcy flux, which is rho v, right, for Darcy flux. And then we multiply it by the mass fraction of component L in phase alpha, so that you get the mass flux, the Darcy mass flux for that component, because again this is equation I. And then for number of components, for NC number of components, you have NC equations, because it's one equation for each of the components. And then we already talked about this, which I wouldn't talk about here, for the diffusive flux using Fick's law. And these are some constraints, right? mass fractions will sum up to 1, right? For all components in all phases, each of them will sum up to 1. So those are 3 equations basically.